Today I'm going to be talking about Dijkstra's shortest path algorithm, which you might find is an algorithm that is more useful than depth first search and breadth first search, which are two algorithms that I've mentioned in previous videos. So Dijkstra's algorithm is an algorithm to find the shortest path on a non-negative weighted graph. A weighted graph is just that the distance between two of the nodes has a value. And it can either find the shortest path between an initial node to every other node, or from the initial node to a goal node. And it remembers tentative distances, tentative being something that could be changed, and it compares the distance between the nodes, using the shortest distance as a starting guide when you visit each of the neighbors. And then once the node is visited, it won't be checked again, so it's final. Now this might be a little bit confusing at first, but once I get into the example, I think it'll make a lot more sense. And some of Dijkstra's algorithm uses can be to find the shortest path between two cities or two different locations in general, like in Google Maps, or with telephone networks and finding this fastest signal route, or even in biology, where the weight is like the length of a molecule, and then you can find the shortest length or strand of molecules, or you could even find the distances between surface of molecules. There's a lot of uses for Dijkstra's algorithm. But first, here is an example. Our starting node is 1, so the value at 1 is originally 0, and because all the other nodes haven't been discovered yet, their values are infinity. And so the only way to change the value of each of the nodes is to find a value shorter than the one in the chart. And to be clear, on the left side of the chart are the nodes, 1, 2, 3, 4, 5, 6, 7, and the right side are the distances or the values. And all of them have infinity at first. So you have your first node, and then you explore the nearest neighbors or the adjacent neighbors. So you go from node 1 to node 2, and that has a weight of 2. So I update the value in the graph to have the weight or the distance from starting node 1 to 2 as 2. And now you go back from 1, and another neighbor is from 1 to 4, and that value has 3. So once again, I'll update the chart. And then you have another neighbor, which is from the first node to the third node, and that has a weight of 5. So I'll update it from the chart. And so now all of the adjacent nodes are visited, so you can say that the first node is fully visited. And you can see on the chart how I bolted it because now it can't be checked again. So you next move to a different node, and the node is chosen by the smallest value in the chart. So we'll go to node 2, and you explore the adjacent neighbors from node 2, and the only other one that hasn't been explored yet is 5. So now 5 will have a tentative distance of 9, and the way I got 9 is because you look at the previous nodes and the path then, and you just add up the distances. So because from 5 you came from 2, and 2 had a distance of 2, you add 2 plus 7, so it'll be 9. And now because all of 2 have been visited, you can cross that one out. It's no longer going to be visited in the future. You go to the next lowest value, which is 4, and from 4 you can visit 5 again. And like I said before, how you add up the previous values, the distance from 1 to 5, the lowest value is going to be 5, because you go from 1 to 4 to 5, as opposed to 1 to 2 to 5, because that path is longer. So from 1 to 4 to 5, the distance is 5, and so now you just change the value in the chart from 9 to 5. Now you go to the next neighbor of 4, which is 7, and now the distance from starting node 1 to 7 will be 9. You can say that all of the nodes from 4 are visited, and thus 4 is totally visited, and then you go to the next node, 3, and from 3 you can go to 7 again. And the distance to 7, the shortest distance, is still 9, so you don't really change anything. But because all of the neighbors of 3 are now visited, 3 is fully visited. Then you go to the next node, which is 5, because 5 has the smallest distance compared to the remaining nodes. So from 5 you go to 6, and that has a distance of 2, but the total distance from the node 6 will actually be 7, because you have the distance from 5, which was 5, and you add that 2, so now you get 7. So this means that the shortest distance from 1 to 6 will be 7. And so now that the nodes adjacent to 5 have their tentative distances, you can say that 5 is visited. The next node you go to is 6. So from 6 you go to 7, and then because the weight of that is only 1 unit, the distance from 1 to 7 has actually changed to be 8 instead of 9, because from 6 the distance was 7 and you're just adding that 1. So now the total distance from 1 to 7, the shortest distance, will be 8. So now 6 is visited and the last node is 7, but because all of the adjacent neighbors from 7 have already been visited, you can say that 7 is fully visited. And now the entire graph has been visited, so Dijkstra's algorithm will be over, meaning that you have found the shortest distance to every node from that starting node 1.